Welcome back to your sensei's digital dojo, my senpais, where we're going to simplify coding one algorithm at a time in my Conquering the JavaScript Interview series. In this episode, I'm going to be cracking the code on the bitwise and of numbers range, a puzzle that challenges your grasp of binary arithmetic and bitwise wizardry, essential tools for any kind of software engineer or people who are just kind of curious and like to learn, like myself. So whether you're getting ready for a weird interview or you're just fueled by curiosity, I'm leaving that in. This episode has got you covered. As always, shout out to Covalence. We have a community membership link in the description down below where you can get access to over 300 hours of our lectures, walkthroughs, and labs in our full stack web development program. We have it broken up into a front end and back end course, and I also have a comprehensive Zero to Hero React course. You're going to get extensive resources, a vibrant Discord community where you actually get positive and supporting mentorship from me, other Covalence alumni, and staff here in your coding adventure. So if you're ready to elevate your skills, learn new stuff, or just sharpen what you already know, consider joining our community and give it a look-see. But let's get back to decoding the mysteries of all this Bitwise stuff, which I'm starting to run out of steam on this subject in my Bitwise Basics series. This one's a little bit more advanced, but it's cool to know nonetheless. Actually, it's not that advanced. It's complex at first, and then once you see the code, it's not that bad as always. So this one's fairly straightforward. We're going to be implementing a function that finds the bitwise and of all numbers in a range. And we're going to be doing this not by iterating over every single number and just adding it to the and bunch. We're actually going to do it in a clever and cool kind of way that will show you a fundamental way of interpreting binary numbers and how to look at them. So our inputs for this function are going to be two integers where they're going to be greater than 0, and m has to be less than or equal to n, and n has a maximum value of integers in JavaScript, which is like 2 to the 31st minus 1, so basically a massively large number. Basically, they're going to take two inputs that are integers, positive integers that represent the start and end of a range of numbers. And our output will be a singular integer number that represents the bitwise and operation of all numbers in that range inclusive, meaning we will include n. So if our input is 5 and 7 right there, we would get 5, 6, and inclusive 7. So we would have to determine the bitwise and of 5, 6, 7, which is simple to think about if you already begin to think, oh, I see an and diagram up there, how am I going to use it? So there's a trick this time. Got y'all. So basically, it's going to handle large ranges very quickly and easily, and we are not going to directly iterate over each number to perform this and operation, right? It's not very efficient for large values, so we're going to go ahead and do it in a very cool and interesting way. So, I mean, at first sight, we're going to take 5 and 7. We know the output is 4, so we're going to go ahead and roll with that one as our number. Before I begin writing the function, let's go ahead and write out what this code would do. It would need to take 5, 6, and 7. Let's go ahead and space these out like I normally do in my videos. So basically, we are kind of pseudo-coding our way through what this algorithm is going to do, right? It is going to basically look at the range of numbers. So this is, 5, 6, and 7 inclusive as our range of numbers for the first input, which is, calling it with input range 5, 7. So if we're calling it with that, and we do an AND modifier or an AND gate on all these things, what do we wind up with? All right, I'm going to go ahead and equal signs. It makes more sense. There we go. So this is our input. These are what the range of values are in binary, and if we did an AND operation on each, remember, AND is this bullet with a flat bottom on the end of it over here. It takes A and B and ANDs them together. We're going to think of it as a very strict security guard at a club. If neither person has a VIP pass, they ain't getting in. If one or the other has a VIP pass, but one is missing, they still can't get in. It's a very strict security guard, unlike the OR guy. If both bit and byte in my little analogy here have a VIP pass, they get in for a 1. So it's fairly straightforward. If there's a 0 anywhere in this column of numbers, it does not equal to anything. So in the left-hand column of bits that all match together, that's definitely a 1. There's a 0 here, so that zeroes out. And then this column also zeroes out. And that is our answer, which is 100, or 100 rather, which is the binary value of 4. So we have now pseudo-coded out what this algorithm needs to do. And like I said, the constraint here is we can't iterate over each individual number and just AND it into the bunch, right? It's not going to work the way you think it does. And again, we're going to be doing some cool trickery here instead of what we just did. So we have now visualized the binary representations, and we've shown what they all share in common here. What's interesting is that they all have a common prefix, right? Which in this case is just 1. So if we shift over everything enough, they all share a common prefix of 1, right? If we shift over 2 spaces, they have a common prefix over here of 1. And anything else that's not a 1, we know with the AND operation eventually just zeroes out, right? So a bitwise AND between any number and a number with a lower value. Because remember, in binary, lower values, if we look at here, this is 7, which is all 1s. Anything lower than a 7 or lower in value will have zeros somewhere in there, right? Somewhere in there will exist zeros in that number. And with the bitwise AND operation, it will probably zero out the least significant bit. So just remember, the least significant bit is just something that appears on the right-hand side. The least significant bit, or sometimes the LBS, is the binary representation of a number that is furthest to the right. So in this case, of 5, it's 1. On 6, it's 0. On 7, it's 1. So that's our least significant bit, with the left-hand side being our most significant bit. So in the context of binary numbers, we have a term here called the common prefix. It refers to a sequence of initial bits that 2 or more binary numbers share, starting from their most significant bit to the point where their bit values diverge. So if we have 2 binary numbers, 100 and 1101, the most common prefix these two share between them is 110, because at that point they diverge to 0 and 1 respectively. So that's our common prefix in this set of numbers. Okay, so we're going to be using this to our advantage, as well as, like I just said, any number lesser than itself will eventually zero out, which means if all the least significant bits eventually zero out, except for the most significant bits that they share, in this case just the left-hand column, all we need to do is constantly shift over or zoom out of these number ranges until we find what they share. And when we have what they share, that means they are then equal with what they share, and all we have to do is count how many times we zoomed out or shifted over. Right? So that's the trick here. We can reduce both numbers by shifting them until they're the same, until we find their common prefix. Once the beginning and the end inclusive number are reduced or shifted or, like I said, zoomed out is how I'm looking, how I think about it. Once they're both zoomed out sufficiently, we have their significant bit, and if we track how many times we zoomed out, we simply shift back in the other direction, and that should be our inclusive bitwise AND range, right? So shifting to the right is going to be like zooming out to see what numbers fundamentally have in common with their higher order bits. We'll keep on shifting to the right until we find what they share. When we have that, we simply tack back on the number of shifts to that common prefix. So while M is not equal to N, or A and B, whatever you want to call our 2 input ranges, what do I call the function again? Range bitwise AND. I keep getting it backwards. Not that it really matters. We can do A and B or M and N for our range of numbers. It doesn't really matter what we call it. Again, they're just inputs, or that's what they represent. So basically, we're going to keep shifting right until those 2 values are equal. We're going to keep track of how many shifts we've done, and once we have that, when they're equal, we're going to stop it and simply take that common prefix, which at this point doesn't matter which one we use because they're going to be both shifted down or zoomed out. And then once we have that, we shift back opposite direction, so left hand shift a number of spaces back, and we wind up with the same answer. So basically it's this with less steps. So here's how that's going to be done. We need to count the number of shifts outside of a loop. We don't know how many iterations we're going to do, so we're going to have a nice while loop instead of a for loop in this case. We're going to continue as long as M is less than N. And all we need to do is, like I said, take each number and reassign itself to be a shifted version of itself, which we can just shorthand to the following right there. So take M and reassign M to be itself left shifted by 1. Same thing for that. Remember, shift left is like that conveyor belt where we move all of our bits to the left and add zeros at the beginning. No, it's right shift. I don't know why I kept saying left. Oh my goodness. Yeah, because we shift to the right. We shift to the right. Yeah, oh my goodness. The arrow, okay, I gotta remember it's pointing the arrow is not less than, greater than. We shift right, which means, I was like, that doesn't make sense. We destroy the least significant bits, add zeros at the beginning, which we know means nothing. And all we're doing is shifting bits over to the right until we wind up with that common prefix, which is our goal here. My bad there, y'all. Right shift. It's a right shift, Luke. And like I said, we have to keep track of the number of shifts. So basically, just every time the loop iterates, that is going to be one shift on our set of numbers that we are right shifting on. Then all we need to do is return either of the numbers, because once they're equal is when this loop ends. So I'll just go ahead and pick M. And we're going to left shift it. Remember, the arrow points this way. The arrow points in the direction we say it in. I've been telling myself that all day, and I can't believe I still mix it up on video. Future Luke editing, if you edit this at all, don't remove the mistake. Just leave it in there because you're human. What are you going to do? I like leaving in my mistakes, right? So we're going to then left shift back the number of shifts we counted, and that's all we have to do. We basically find the common prefix, right, by right shifting each of these numbers by 1, track the number of shifts, and then simply take the common prefix and then move common prefix back to its original position. With the number of shifts we shifted to the left, we shift back an equal number to the right. And guess what? That's all we got to do. So if I console log range bitwise and 57, save it, we get an output of, let me get rid of that stupid console log. Is this thing on? Yeah, and there you go. That was the expected output we expected to see. When I put in an input of 5 and 7, it took these three numbers and ran an AND operation on each of its bits and wound up with 100, which is indeed 4 as our expected output. Except this did it in that clever, tricky way when I told y'all to remember, any number less than itself has zeros somewhere in its least significant, or the right-hand side, bits, which means with an AND operation, they have to zero out because that is how an AND operation works. And then we learned that if we simply focus on their most common prefix, we can then logically take that prefix and simply move over a number of bits, push it to the correct number of bits it needs to with those shifts. And those two interesting pieces of information together is how we piece together this algorithm without actually iterating over each number. So something I haven't mentioned in this one is, again, this seems like really weird because why would you need to care about the bitwise and range of numbers? We'll get there as always. There's actually a very specific thing this is used on, and I'll tell y'all. But yeah, I just wanted to point out that it does work this way with this trick. So let's actually do what I normally do, as always, which is take down how this ends up working. So we wrote it out by hand up here, but again, this would be ridiculous to do by hand or in logic. If we had a very large range of numbers, it would take me a very long time to write out all the numbers, all their binary representations, and then attempt to AND all of their columns, which again, at the end of the day, if there's a 0 in that column, it won't matter because it's going to equal out. It's going to zero out anyway. But let's actually do what this one does. So if our M is 5, that is a binary 101. If our N is a 7, which is 111, we know that's our starting values right there. Then here we go. We're going to go through iteration 1. Shift is, well, we haven't done shift yet. So we'll do iteration 1 of our while loop. Shift starts at 0. Remember, this is going to be our first count in our shift. So if M is 101 and we left shift that by 1, it gets us a new M value of simply 10 because we shifted over to the left. To the right. We shift to the right. One time, I was like, why am I saying left still? Because I'm an idiot, that's why. Okay, we shift to the right 1 bit. So there we go. We simply truncate that down to a 1, 0 on our right shift. In this case, right shift by 1 bit, we're going to get a Juan as our new value here once we perform the right shift. And then our shift counter goes to 1. Okay, there we go. So next we go to iteration 2. M equals 1, 0 from our previous iteration. If we right shift that by 1, we get a new value of 1. 1, 1 is our previous N in the previous iteration. Right shift that. I don't know why my brain is trying to make, it's because I'm overthinking it now. Like because my brain is like, panicked that I keep saying it wrong, I'm going to keep, it's like self-fulfilling prophecy here, folks. If I right shift it, we get a 1. There we go. Because remember, it will simply take that least significant bit, blow it up, and shift over the other bits, which is exactly what it does. And we get a 1. Remember, we can theoretically, in our mind's eye, think of simply adding zeros at the beginning, but for the representation purposes of the number, it doesn't matter here. So we're going to shift everything down to 1. And guess what? Our shift goes to 2. And hey, I forgot to be asking what our iteration was, which is m less than n? No, they are now equal. So guess what? We have made them equal, which means we have found their common prefix, and all we need to do now is shift it over by 2. So we take m, which is a value of currently 1, left shift it by 2, and that gets us 100, which is our binary representation of 4 and the value we expected to see. And there you have it. There is the magic at work. And we did this iterative process not for every single number in the range, 5, 6, 7. We simply took the 2 numbers, shifted them to the right until they were equal, which means we found the common prefix. And then from there, all we had to do was count the number of shifts we did, take the common prefix, and shift in the opposite direction, which is left, the same number of shift positions. So let's do another one right down yonder. There's a trick question here. 0 and 1 is a range. Remember, anything ended with 0 winds up with 0 anyway. So remember, if that's ever a question you encounter in an interview, probably not as a web developer, but you never know. You never know what crazy questions interview places can ask. There have been comments, and I've got, as long as I've been teaching at Covalence, almost like 6 years now, I get asked questions like this regularly, which is like, am I really gonna get asked something like this in an interview? And unfortunately, I would love to be in a world where I'll say, probably not for a web developer interview. I'd be highly surprised. But over my years and seeing all these alumni that have gone through our course and gone on to get jobs and bombed interviews, destroyed interviews in a good way, succeeded in them, for example, and gotten a job offer and things like that, the questions places ask are simply ludicrous. I feel like some places ask questions that you're not meant to get on purpose. Someone's got an axe to grind. They just don't like you. You can't help that, right? But as always, like I say, luck is where preparation meets opportunity. I think this is just cool to know, and it does improve your fundamental understanding of computer science. So for individuals that didn't have a computer science background in school and learn web development and are now kind of backtracking into the basics of how a CPU works and this binary stuff right here, I find this simply fascinating. And again, if I ever find a spot to shoehorn it in during a discussion, you bet your bottom I'm gonna. All right, so the 0 and 1 was a trick question, and that is just, well, anything ended with a 0 will always result in 0, so 10 and 15. Yeah, we'll do 10 and 15. We'll do 10 and 15. Okay, so 10 and 15. 10 and 15 gets us 8. Was that the right answer? I didn't even look at the right answer. Yeah, it's the right output of 8 is the expected output for the bitwise AND of 10, 11, 12, 13, 14, 15. So I'm not going to write out all 6 numbers and do this right here. Like I said, I've already gotten lazy. So what we're going to do is do the same operation down yonder. So what I'm going to do is I need to change this back to 5 and 7. We're going to leave that there. We know that's the 4. Paste this yonder, and 10, 15, we know that's going to be an 8. So here we go. So our M is 10, which is a binary of 1, 0, 1, 0. Our N is 15, which is 1, 1, 1, 1. There's a reason I picked these numbers, so I can actually memorize their binary outputs instead of having to pause the video or edit it later and come in or pause the video with an edit to remember what they were. And that's our starting input. So let's get this sucker going. Iteration 1, here we go. M is 1, 0, 1, 0, and we right shift by 1, which gets us a 101 as our number. In this case, I think you all can already see the common prefix again is 1 over here. So we're going to say 1, 1, 1, 1. Right shift 1 gets us 1, 1, 1, and our shift counter goes up to 1. Iteration 2. Our M is now 101. We right shift that by 1 and get 1, 0. N is going to be 1, 1, 1. Right shift by 1, 1, 1. Saying this out loud is so funny. Shift 2. Iteration 3. m equals 10 from the previous iteration. Right shift by 1 gets us a new value of 1. N is a 1, 1. Right shift 1, also a 1. Shift counts up to 3. And as you have it, m and n are m is no longer less than n, which was our condition from the original code, remember, up here. M is less than n. So now it stops the iteration. We can pick either one. We can pick m, which is 1. Left shift, however many spaces. And that gets us 1, 0, 0, 0, 0, which is the, indeed, binary value of 8. There you go. So there's how it works, and I think it is pretty darn cool that it works that way. So as always, this will be available in a Codepen for you guys and gals. If you wanted to go ahead and grab this and have it on your machine, build your own directory add or something like that. Remember, bitwise operators, if you had to give it an interview, think of control switches as on a Christmas string lights. You can control them with and, ors, unique ors, or zors. Not, as in flip all, ons, off, etc. Left shift, right shift, like we saw here. Remember, the direction of the arrows is left shift and right shift, right? So don't get it wrong like I did in this video. Remember, whichever way they're pointing is which way you're shifting. Don't think less than, greater than, like my brain kept trying to do. So they're really good at data manipulation, setting flags, encoding, decoding, any scenario when you need to work directly with the bits of a number. They're very specific tools in the programming world. Now, space complexity, in terms of big O, right? We already know that because I don't see any kind of large growing data structure, just this kind of singular number value that will grow over time with iteration count, I can tell you that easily that the big O time space. So the big O space, we can easily see right here as a 1 because you're like, oh yeah, well, you know, that's going to be a constant growing space. Not even growing, it's a constant space. I don't know why I threw the word growing in there. It's because it has a fixed amount of space to store a small constant number of variables, m, n, and the shift counter, regardless of how big the input range is. No additional space will scale with the size of the input, right? So it's always going to start at 0 shift count and grow from there. M and n are two numbers. Left shifting them is not going to make any new space. It's a constant. It's not making new variables for each iteration, right? It's simply counting things up, no additional data structures like array or objects who would vary the size of the space complexity. So you would think, you're like, okay, Luke, I see a loop in here, which probably tells me we're going to have something like that maybe, or some kind of logarithmic scale if I'm just taking random guesses here. Did I get rid of my big O diagram? Where'd you go? There it is. You would think that it might have something around this range or n at worst, going, well, the bigger the range of numbers is the more iterations you would have to do, right? That's what your guess would be. And that's what my guess was as well until I kind of looked into this further. But it's actually a big O of 1 with the way we have it solved. And you're like, what? That doesn't make sense because it would depend on the range between m and n. That would be the number of iterations, right? But remember, the efficiency comes from reducing the problem to find a common representation, or common prefix rather, of binary versions of m and n. So the number of iterations to find that prefix is proportional to the number of bits in the numbers, which is constant. How are all numbers actually stored typically in JavaScript? 32 bits for standard integers in tons of programming environments, JavaScript included. So if they are 32-bit integers, that is the maximum number of iterations we'd ever actually go over, right? It doesn't scale with the size of the input range, but it's actually constant depending on the fixed bit length of the integers, which again can only be 32 bits total ever. So, and that's how they're all stored. Like there's still like a whole leading set of zeros and a signed bit at the beginning to tell if it's positive or negative. So it's it works out pretty cool. And it's one of those trick questions of the time complexity. Because again, you see a loop, you see, oh, in a range of numbers that would loop that many times. And the bigger the range is, the more the loop would grow. But remember, we're thinking in binary, 32 bits always. And that's the trick and fun part of this one. So I told y'all there's actually a specific use case for this beyond just, oh, you get to learn something, herder. You actually can use this in network address calculations. So in networking, determining a network's given IP address and a subnet mask involve a bitwise AND operation. The algorithm can be applied to calculate the starting address or network address of a subnet, which is essential for segmentation and routing in your networks. Your common permissions and security, your common blah, 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 data compression, encoding, optimizing, all blah, 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 right? That's all the fun stuff. But again, you have a specific use case for this, which is in network address of a subnet, which I think is pretty dang cool. It has such like a direct corollary to something in the real world. So again, in terms of elegance, simplicity, efficiency, deeper understanding of your binary arithmetic and how a computer actually works under the hood, how your programming language is actually doing things under the hood, the versatility and, again, interview and problem-solving skills are all sharpened by trying to actually learn this stuff. So, as always, that's a wrap on today's binary adventure. We've traveled through a lot of zeros and ones. We've unlocked the secret of this particular algorithm, and it's amazing how a simple concept can reveal so much about efficiency and elegance, isn't it? So, hopefully added a new tool to your coding arsenal and also sparked a deeper interest in the beauty of just computer science. Remember, every challenge is an opportunity to grow, and with each problem we solve, we are one step closer to mastering this art of coding. So don't forget to hit the like button if you learned something new today, subscribe, and hit the bell notification for more coding mysteries unraveled as I go through random things I find in here, random comments I get, or random Discord discussions I have. If you have any of your own algorithms you would like to see solved, given an analogy or helped with, or anything cool you come up with Bitwise stuff, drop a comment down below. Your challenge might just be the star of my next video. So until next time, happy coding, and remember, best way to predict the future is to invent it.